All right, in this video, we start by defining a unique factorization domain. So a unique factorization domain, or UFD, is an integral domain with two properties. The first property is that if you have a non-zero non-unit in your ring, you can break it up into a product of irreducibles. And two, that product of irreducibles is almost unique. If you have two products of irreducibles, then the number of irreducibles n and m have to be the same, and bi and c sigma I are associates for some permutation. What this condition is saying is that the list of irreducibles here and the list of irreducible here are pretty much rearrangements of one another, up to associates. So let's see an example. The motivating example is the integers. So the integers are a UFD, that's for sure, because of the fundamental theorem of arithmetic. Any integer can be written as a product of primes. So for example, 24 is 2 times 2 times 2 times 3. And that's pretty much the only way to write 24 as a product of primes, up to some trivialities. What I mean by that is 24 is also 2 times negative 3 times 2 times negative 2. What I did there is I just mixed up the order of these irreducibles, these primes, and I threw in some units, -1 a couple times. It's really kind of the same expression, just written slightly differently, so we consider these almost the same. That's why it's a unique factorization domain. Let me do another example. Maybe to contrast, let me do an example of a ring that is not a UFD. So I'm going to look at the integers adjoined 5 times root I. So these are almost the Gaussian integers, but I've scaled the imaginary axis by root 5. So this is all elements of the form a plus 5bi, excuse me, root 5bi, where a and b are integers. So you could depict these graphically in the complex plane. I've tried to do that over here. So here is the real axis, here is the imaginary axis, and I guess the distance between two rows of dots here would be the square root of 5. This is not a UFD. There's not a unique factorization. Why? We see that 6 is an element in this ring. 6 can be written as 2 times 3, but 6 can also be written as 1 plus root 5i times 1 minus root 5i. So I could break 6 into irreducibles two different ways. So you could check that these 4 elements are all irreducibles in the ring. You could check that by a geometric argument. We gave a similar argument in a previous video that when you multiply by an alpha in this ring, the magnitude can only increase because in this ring, except for 0, the magnitude, the complex magnitude, the distance away from 0 of every point is bigger than or equal to 1. So when you multiply by any non-zero element in this ring, you increase the magnitude of what you're multiplying by. So you could just check every number with complex magnitude less than 2. So here's 2 in the ring. You could check all the numbers with complex magnitude less than 2, and there's no way to write 2 as a product of non-units multiplied together. Same thing with 3 and these two terms. So here would be 3, and right here this would be the point 1 plus root 5i. So So anyway, you could argue that all of these are irreducible, and therefore I do not have a unique factorization domain, because I could write 6 as a product of 2 different irreducibles. Okay, so that's a unique factorization domain. I'd like to finish this video with one other definition. So here's another definition. A principal ideal domain, and this is abbreviated PID. So a principal ideal domain is again an integral domain such that every ideal in D is principal. So remember the definition of what a principal ideal is. A principal ideal is an ideal that's generated by a single element in the ring. So every ideal is simply terms of the form AR, where R is in your ring. So that's a principal ideal domain. Here is an example. We've already proved that if you have a field, then polynomials over that field is a PID. That was one of the theorems that we proved about polynomials over fields. They're generated by a single polynomial. Let me give you a non-example to finish this video. So a non-example could be, I don't think we've done this before yet, polynomials in 2 variables with rational coefficients. So just to give you an idea of what elements in this ring are, it's just polynomials with 2 variables, rational coefficients, so I could get 2x squared y plus x plus 1/2 y plus 1/3. So that's a polynomial in both x and y variables, rational coefficients, and so on. I claim this is not a PID. So this is not a principal ideal domain. Now, to show you that it's not a principal ideal domain, I need to come up with an ideal in the ring that's not principal. So I'm going to say, take your ideal I to be the polynomials p of x, y in your ring, such that if you evaluate at x and y equals 0, you get 0. So these are all the polynomials that would have constant term equals 0. So I claim that this ideal I, it's not difficult to prove it's an ideal from the definition of an ideal, and I claim that this ideal is not principal. It cannot be generated by a single element. Well, this ideal cannot be generated by a constant, a non-zero constant like 1/3, because a non-zero constant is not in the ideal. So if this ideal was to be generated by a single polynomial, it would have to be a degree 1 polynomial. But no single degree 1 element polynomial can generate I, because then x would have to be an I and y would have to be an I. So since x is in I and y is in I, no single degree 1 polynomial generates this ideal. So that proves this is not a principal ideal domain. So in this video, I've defined 2 things: a unique factorization domain. When you think about that, think about products of primes or irreducibles, just like we have for the integers. And we also defined principal ideal domain. That's a very nice property where every single ideal that you could find in your ring is principal. The ring of polynomials over a field is a perfect example of a PID. So the goal will be to show that every PID is also a UFD. So we will prove that every principal ideal domain is also a unique factorization domain in videos to come. All right, I'll see you there.